Okay. In the name of God, the compassionate, the merciful, this is going to be session 2 from our or week 2 from our C++ template metaprogramming session. I am now going to share my slides. Okay. Right. Okay, so any questions from the previous sessions? Has anyone been able to read through the chapters that I taught?
I was
There were
reading for
quite some. So like the first 4 I taught in 1 week. Has anyone been able to go through them? No?
Working my way through, not completely
Oh, very good.
caught up.
Okay. Is there any way you stuck that you need help on?
No, just I think it was just be nice to have like a little overview of what we're covering and which chapters to go through, just for my own studying's sake.
Right. Okay. I'll provide that. I'll provide that. Just you know what? The best idea is that you send me an email and I will respond to the email with the
Right.
Yep.
Yeah, I can do that.
Okay. So the idea of this C++ template metaprogramming is to focus on template metaprogramming, and therefore I'm not covering all the book. In fact, I'm covering only very little of it, especially because we can't go very deep in the C++ TMP. It's a very deep topic. But so last week we saw function templates, we saw class templates, we saw non-type template parameters, and we saw variadic templates, right? These 4 we saw last week. And this week we are going to see kind of usages of those as of the means for doing template metaprogramming. Now, I'll start by reminding you that, why is this not picking up with me? Hello? Oh, it has a latency. Okay. Right. Oh, the latency is high. Well, anyway, I would start by speaking to you about 2 subjects. One of them I will only briefly mention because it shows up in the slides that I'm using, but you only need to know about it so that you understand the slides. This is not something that you need to understand. You don't need to have a good understanding of for this module. Now it's a nice thing to know of, but it's not something you need for this module. And that's move semantics. So move semantics is the one that I'm going to only briefly allude to. Then we'll have a few things about enable if, which is such a syntactic noise, but you need to know about it. So let's say that let me see. In the interest of coloration, I am going to go for blue. Yeah, blue is good. Okay. Let's say that there is a class called X, and you can pass that class by reference, like it is being done here. So what G is saying is that when I am called on a member of sorry, on an instance of class X, do not make a copy of that instance. Just you know, get hold of a reference to there, and I will do my changes in place, right? So that's that. There is something else which came out in C++11, and that's, by the way, these numbers. C++11 is C++ standard of 2011. So right now the latest standard is C++23, which is for 2023, right? Now, so this one, this overload of G is saying that if you pass an instance of X to me, I will not make a copy of it. I will not take a reference to it, but I will assume that you allow me to steal the GOTS of that instance. So, for example, if I have a let's say that we have an instance X and another instance X primed, right? If I call, well, this is going to be a bit ugly, but let's say if I call this, which then produces for me an instance of X reference, then this overload, the second overload, will be called. Now after that, we say that X is in a X is well, I forgot the terminology.
Pointer reference.
No, it's
After
the call. After the call, X is outdated, invalidated, right?
Validated.
Which means that you can think of it in terms of the managed languages as of this being a null, right? So it no longer is the working, like if I want to send X itself to G, by which calling this first overload, then my program is ill-formed, because X after this call is no longer a valid variable, right? Unless I give it some GOTS from somewhere else, right? Now, so that's an instance of so let me just get rid of everything. Come on. Right. And now, so this syntax is for when you want to. This is called an auger donation, right? So this is saying that, okay, the instance of X which comes to this overload of G has agreed that at the point where it's being called, it will be invalidated, right? That's called move semantics, right? Because the GOTS of the instance will be moved at that point, right? Now, this is all you need to understand about move semantics. It won't really show up in what I'm going to teach you with template metaprogramming. So That should be it. Now, so I told you about classes and about the differences between the differences with struct. Just very briefly, it's very common for classes to have constructors, and constructors in C++ have the same name as that of the class. So it's a member function. This guy is called person. These member functions, they have the name person. So they are all constructors of the class. So what you're seeing here is 4 different constructors for the class person. Now, 2 of them are marked explicit, right? That means that if I want to do like a person P of test, that's fine, because I'm being explicit about P taking a string, because then this overload will be called. But if I have a, let's say if I have a function f which takes a person, a reference to a person, for example, then I can't say f of test. Whereas if I didn't have this explicit keyword here, what would have happened would have been that, okay, string would have implicitly been used for constructing an instance of a person using this instance, this overload of the constructors, and then that implicitly created person would have been passed to f, right? So explicit says that no implicit conversion using the constructors. That's what explicit is instructing the compiler with. Excuse me, I'm one moment. Record. Okay, so Daniel, were you able to follow the usage of explicit?
No, not
No. Okay.
not really.
Okay. Do you see that when we are using a string here,
Yeah.
to create, oh, this is not a string itself, this is what is called a C string,
String literal.
Yes, string literal. But suppose that well, let's put it this way. The reason why you can implicitly convert a string literal to a string is because it has a string has a constructor which is not marked explicit.
Right. Okay.
If it would have been marked explicit, then even this first line would have not been possible.
No.
Right.
Okay.
So that's the entire idea.
Yeah, I think that makes it more clear now.
Okay, good. Good. So that was that. Now, so the idea here is that we have 4 different constructors, and 2 of them are explicit. One of them takes its argument by reference, by a reference to constant. So in C++ there is this right to left convention that some people use. I don't use myself, but it's easier to read. So for example, it's more clear here that this is a reference to a constant string, because you read it from right to left, right? Whereas I would usually write this as const string reference, right? Now, this is a matter of preference, and I can definitely buy the idea that what is on line 7 is more readable because it's consistent. Now, so what else? The other reference is the second overload of the constructor takes it by by what is called the R value references, and that's because it's using the move semantics. Now, inside, let me just do one thing at a time. The one that is not the first one that is not explicit is let me see. There is a right. Then so the second pair of constructors are what is called copy constructors and the move constructors. So you see the difference between these ones, the first two, and the second ones is that these guys work on strings, so they receive strings as their parameters to constructors, whereas here we have another instance of the class person itself. That's why this is called a copy constructor. So if I have like person P1 and P2, and I do a P1 equals P2, or no, sorry, that would be an assignment operator. Forget about that one. So let's say that I have a person P1 of, let's say, Ali, and then I do a person P2 of P1, then the intention is that in the instantiation of P2, this constructor would be called.
Mm-hmm.
And in the same way, I can produce an explicit what is called an R value reference, so that then this one would be called, and therefore, you know, its GOTS will be moved upon the creation of the newly constructed instance. Now, again, I need to teach you some C++ syntax. So now, one thing to notice is that internally a class string, an instance of a class string, has a data member called name, which is of type string, and that name thing needs to be well, the constructor is supposed to initialize that name thing. And so the syntax for that is that you see this colon here. It's initializing the name data member of this instance that is being constructed using this n, which is what it gets from here. Right, so that's the syntax.
Isn't this usually done in the body, or?
Well, that's a very good question. So the body is called after the initialization of the data members, which means that yes, you can change that but you can, one thing that you can do is that you just remove this, and somewhere in here you write name equals to n, right? You can do that, but if you do that, then at the point where the flow of execution enters this body, name is already constructed. And therefore, when the flow of execution makes it to here, it no longer is initializing anything, it's copying, or it's assigning, sorry, it's assigning n to name.
Yeah.
Right? So that's the difference between where you put that, right? Now,
Okay.
That's only possible in this very case because the class string, right, has a default constructor, which means that you can construct an instance of string without passing any arguments. Right? Now, some classes are not default constructible, which means that if you don't initialize them properly before the body of the constructor, the compiler will catch you.
Okay.
Right? Now, that's don't mind if you, I mean, you don't need to know all that for this module, but just because you asked the question. Now, let's go back to blue. So, and now we would like to see instances of when, oh, I don't have instances. Oh, okay. Now, let's say that we added another constructor. Now, constructors are also like the other functions. They can be type parameterized. So now we have a fifth constructor, which is parameterized by a type that we are going to refer to in this constructor by using str. That's also an explicit constructor, and it takes its parameter by R value reference, which means that it will steal the guts of it, right? Now, and so it does the what is called the perfect forwarding. You don't need to know that. This is all you need to know is that this oh, come on, stop it, please. All you need to know about this is that it gives you the move semantics. This is to make sure that the move semantics works correctly. But now, so we also have the copy constructor and the move constructor, right? Now, one thing which is important to you to know is that so like every other function, when we have different overloads of a function, the rules of overload resolution of C++ kick in, right? And that means in particular that, you know, if you, let me do it this way. If you pass a non-constant instance of person, so if I have like person P and I do a person P primed that I would like to initialize using P, right? because P is not constant, it's a better fit. I spotted a yawn from Jan.
Yes, definitely.
That I'm gonna write yawn number 1.
You can
Now-
attribute it to me as well, if you like. Just shame.
Okay.
Public shame.
Right. Yeah, so because P is not constant, the fit is better for this overload than this overload, which means that you have screwed your copy constructor, right? So we need to find a way of making sure that doesn't happen, right? Now, instead, if I had a let's say let me write it here. So let's say that I had a const person P1, and then I wanted to have a person P2, P1, then in this case, because P1 is constant, then fine, then the copy constructor will be called, because then the compiler sees this const here, and it knows that this is a better fit than the template constructor at the very top, right? Now we don't want, we do want the this to to work as I just told you. What we don't want is this one. We always want, when we pass one constructor to the one instance to the constructor for creation, we want the copy constructor to be called, right? So that's the idea. Now, the book gets into techniques for making sure that you can actually instruct the choice of the overloads, and part of that goes through the mechanisms of enable if, right? Now, that's why you need to know a little about enable if. Now, this is a good time for a joke. So let me see. James, would you mind?
Yes, I can tell a joke.
Thank you.
What was it? My father is encouraging me to get a donor card. He really is a man after my own heart.
Okay.
Good.
Good one. Good one. So, by the way, so move semantics. Like there was for a long time this terminology that when a move happens, the recipient is stealing the gods of the provider. And then Herb Sutter, who is one of the big names of C++, was presenting in one of the C++ conferences, and then he said that, well, this is not a steal, because this is not a stealth, because the one is willingly, so the provider is willingly providing their gods, and then someone in the audience said that, oh, that's a
Organ donation.
Yes, organ donation. And so at that point, he just said, oh, that was a very good terminology. We are now going to call this organ donation from now on. And so yes, it relates to your joke, James, too. So we are now dealing with organ donation in C++. Right. Should we go for another joke? Daniel, do you have one?
Oof.
Oh, it's difficult.
All the good ones I've kind of
Oh.
used. You know why snakes like to such as like pythons like to hunt on land.
They hunt on land.
Yeah.
There are water snakes.
Because they like to stay above sea level. The key word here is Python.
Yeah, because it's
Uh-huh.
because it's
Mhm.
I'm glad that one got
That was
piece
very
of-
good.
That's good.
Right, but that's something you should be able to read in order to, right, okay.
Yeah, sea level. I have to emphasize the sea, really.
That's the homonym. It's very
Yeah.
nice.
Yeah, let me introduce you to something. Maybe you are already aware of this, but this is a good point to introduce you to this. So there is a website called Tiobe.
Tiobe.
This is a Dutch company, the business of whom is ranking of languages. They really make money out of this, right? And let me see. Cookies on, tracking cookies off. Let's see. Now there is this Tiobe index, right? In which they kind of so their business is in certifying languages and code written in languages with the level of goodness, right? Now, but they also make a lot of money by selling their
Data.
data regarding how popular languages are. So they have a huge search on different work engines and things of the like, and queries in internet in different search engines and all that, so that they can come up with this ranking. I'm not taking this as gospel, but I know that these are one of the most serious people who kind of rank languages, and I have been following them for, I believe, perhaps around 15-16 years. So I have already I have always had an eye on them. Now, you are right that Python is at the moment above the sea level, right? And it has been such for quite some time. So if you this is perhaps the more interesting graph. You can see the that they have data from around like 2001, and this is huge data. They so if you for example want to see sea level, or perhaps you want to see Python, there's this point in 2021 or so where Python starts to go above sea level.
What occurred between 2000 or in 2007? I see both Java and C took a pretty nasty dip. 2017, sorry.
That's the point when I think, if I recall that correctly, that's the point when multi-core processors became very cheap. Which meant that productivity of programming is no longer the first priority. The first priority. Yes. Yeah. So the entire reason why Java was the top language for some time was that it came out. This was a very lucky coincidence. It came out right at the point when the processes couldn't get any faster, and therefore people knew that their code cannot get faster than a certain level, and therefore they switched their focus from performance to productivity. Well, that
Okay.
game changed as soon as, you know, affordable multi-core processors came out.
Then it's back to
Right.
performance.
Right.
Yes.
Yeah.
Then performance became the king. Yes. Except that Python is still on the rise because it's accessible to everyone. You don't need to be.
It's like
What
the
was it, sorry?
powerhouse for machine learning as well. So
Yeah.
Yeah.
That,
machine
that
learning
was
trend.
also another. That's true. That was another you know, lucky coincidence. So if Python was just so accessible 10 years ago, it would have not made this you know, ramp up, right? So that's us having some lesson about timeliness. Now C++ is actually very close to the second line. I think it's C. Yes. So if you take a look to the market shares, you know, it's first of all, C++ has in the past years always been on the ramp up, but not that much. But anyway, it's getting closer and closer to the top languages. It's whereas like when I started teaching C++ back in 2003, you know, and that's around here. You know, there was C++ and Java were very close at some point, and then it was clear that Java had a clear you know, overhand.
Yeah.
So for a long time Java was way above C++, and then, you know, that sudden decrease that you just mentioned, Daniel, happened, and C++ began to go up. So, but last year, and this is something that I really like. So they have a you know, Hall of Fame, and so last year,
all the way at the bottom.
It is. Yep.
yeah, C++ was, after 20 years, again the language of the year. You know, so 2003 is when I started teaching C++ in university, and I have been telling people, look, C++ is a very good language. It's just very unfortunate that it's not at the top of the market anymore. But now it again is back, and I'm very happy about that. Yeah.
I mean, it's still valuable
Okay.
to learn, since you see where all the ideas for many of the ideas for the other object-oriented languages stem from.
That's true, but that doesn't buy it a lot of market share. So
And all of the
thank you for
fast libraries in Python are written in C++.
We'll see.
that.
We'll
That's
see.
true. Yeah, that's true. But it's the thing is that this index in TOBE is about the market shares. It's yeah. Okay, if you don't mind, it's a good time to get back to work. Now, so let's say that you have a function foo that is templatized, and you want to make sure that you can only call this function with t's that are that have a size bigger than 4 units of size, and this is usually bytes, right? Now there are a number of techniques, and I have to tell you that enableif is actually a very old no, not a very old technique. It's an old technique nowadays. There are better ones that you can use, but because this is still widely used, I'm going to teach it. So here is one enableif technique that you can use. You can use enableif by saying that, well, by giving this function foo the following return type. Now, this big ugly creator will type reduce to void if it is a valid type. Now your number 2 by James. Okay. Now, so how does it become a valid type? Well, it becomes valid if this condition of it becomes valid, which means it becomes valid if the size of the type with which foo is being instantiated is larger than 4 bytes. Now, another way to do that is to make this big ugly creature the default type argument to an additional extraneous type argument, sorry, type parameter of the, let me do that better. So we're providing a default argument, which is this big ugly creature, as a default argument to an extra template parameter that we are giving to foo.
So it's like we're requiring it to provide a proof that T is of size.
That's right. Yes, that's true.
We don't name that type name.
I will get there. That's true. That's true.
Okay.
Right.
Is there a reason
So-
why we have underscore T after the enable list?
There is. I'll get there as well. But I want you to first grok the technique. Right. So that's one thing.
Similar to a field constructor. Like a dependent product.
The similarity is in the provision of the default argument, I guess.
Yes.
That's right. Yeah, that's true. That's true.
Sorry.
Now let me you were continuing, Jan. You
No, I
wanted to
just
say
said sorry
something?
for interrupting. But yes.
No, you don't need to be sorry. Now, let's focus on the questions that were asked. First, James' question. So if I have a function void f, let's say, that takes int I, and inside, let's say that it performs plus plus I, right? I need to give the function a name. Sorry, give the parameter a name. But if I have another function, void g, which does take an int, but it doesn't do anything with it, I can leave out the name because the name doesn't occur in the body of the function. And C++ allows me to leave that unnamed when you know there is no occurrence of the guy in the body, right? For the same reason, it is true that we can give this a name. Let's say we call this Y. We can do that, but we're not using that name, so we don't need to provide a name for it. In fact, a lot of C++ compilers that are common and that have been around for what I'm going to tell you has been around for at least 2 decades. So a lot of the C++ compilers, if you name something, right, and you don't use it, they will issue a warning so that you know that you were not using the variable that you have just given a name to, right? So that's that. Let's get to Daniel's question. So Daniel's question was
Underscore T.
right. So let me see whether I have this. Right. Yeah, that's here. Right. So there is a, oh no, just the most.
Do you teach
Okay.
him C++ to go to bed?
No, he doesn't. He doesn't need me to teach him C++.
He already knows.
He learns on his own. I learned C++ on my own. He does that too. Yeah. So let's see. So there is an alias, what is called the template alias. I think I taught you that. Yes, I did in the previous session. Which is defined like this, right? Now, so this extra, underline T is saying that, okay, I would like to have the, well, let me do this. I would like to have the nested type called type of enable if of BNT, right? Now this will become more clear when in the practice sessions we do template metaprogramming of ourselves. But for now, just it suffices for you to know that this underline T is just a shorthand. Okay.
For
That's
for when you have like a bool or some expression that evaluates your bool inside the brackets. All right, not the I can't remember what the angular brackets.
Let me just the answer is no, but if I try to explain more of this syntax that you're seeing, or this code that you're seeing, then that will help. Now, enable if takes a compile time Boolean expression, right, and the type T, and the so-called type that it returns as a meta function, and these are things that we will speak about in the remainder of this module, right? The type that it returns as a meta function, which is this guy, will be T, provided that B reduces to true. Right? Now we also have a default argument for T, which is void, right? So that's but the thing is that we this is like a bind. So enable if of B and T is like a bind in like if you do sorry, but it doesn't still perform the function call. So you know which function call you want to take, right? You want to make, but what we haven't still done the function call, right? As soon as you perform this, it is that you finally made the function call, right? There is a sort of laziness that I will get to in few sessions, not few sessions, in the practice session that will become quite clear. Right, this is a good time for me to get into CPP reference. So, but we have in the past seen this website. So why is it not? Oh, so cppreference.com is kind of the official reference for C++. And let me show you this. happening? If I look for enable if here, you see that there are more than 2 techniques here. There are in fact I think 5 techniques for using enable if. Is it? Yeah. So this is technique number 1, technique number 2, technique number 3, technique number 4. I think there is also technique number 5. Yes, there's also technique number 5, right? So this is there are different trade-offs about which technique you want to use, but I'm only showing this to you so that you know that there are immediate things that you can learn which are not in the book, and I'm not teaching you, but CPP reference can be useful for. Okay. Now, let's you don't need to understand the techniques now, by the way. Neither do you need to understand them for the remainder of this module, just for you to know for the future reference. Now, okay, so why do we need to learn about enable if? So you remember that we had a class person that had a template constructor, move semantics, right? That template move constructor that we wanted to avoid the calling of for when I have a non-const instance that I want to copy from. Right? Now, the problem with the previous formation of the constructor was that it was too loose with the instantiation of this first type parameter. Right? Now we want to regulate that. Right? So we want this one to be called, as the name is suggesting, str would be only for types which are string-like, right? And so we want str which is convertible to string. Now there is a meta function in C++ standard which is called is convertible, and that too has shorthands. It has one shorthand which is convertible underline v, which takes the value static data member of. Right, we'll see these in the practice sessions. Right now, so what this is doing is that it's regulating the types with which this template move constructor of person can be used. Right now, that means, for example, that when we perform the call here, when we perform the construction here, then given that if it would have been that P was to be P2 was to be constructed using this constructor, then str here would have been person, but then person needed to be convertible to string, and that is not the case. Therefore, this constructor is not applicable. Okay. Right. Now, I will let you guys have your peace or come to peace with yourself regarding this piece of code. You have 1 minute. Okay, your minute is over. Is anyone at war with that piece of code?
I don't think so.
No. No. James, are you fine with it?
Well, I'm a bit confused that
Okay.
by so you're like sixth, you're passing a person which is supposedly convertible to a string.
No, it is
Oh
not
no, copy
convertible to string.
constructor. So we're using the code from before. If we're using the
That's right. Yeah,
oh yeah, then that's fine.
Mhm.
yeah, so let me get back to I
So
mean
whatever
if
that
you can
type-
recall that. What was it, sorry?
Oh, I was going to try to give a bad explanation. So whatever
Oh.
that type name string, whatever that type is, the type enable if t on line 4 enables an if for that type, and the if is if it is convertible, if str is convertible to string. Is that right?
That's your logic is correct.
Hmm.
Your logic is correct, yes. But
What's the
James, do I
actual
need to go back to the beginning of the slide so you can see?
No, I remember it. It's fine.
Okay, very good. Okay. Okay, good. Now, this is a good time for another joke. Niels?
I was at a wedding recently. It was very beautiful. Even the cake was in tears.
Beautiful. Oh, right, with the beauty, right, okay.
Because you
Okay.
tear the cake and then
Yeah.
no, it's like little pieces of it when you tear it. It's wild.
Sure, sure.
Thank you for explaining the joke, Jan. It
Yeah.
really.
Well, you see, I had to have an exam where I had to justify all my answers today, but I didn't do it.
Oh well. Now you can do one more thing though. You can give us your joke.
Oh, sure. What's the most important part of a joke?
Punchline.
Itself.
Funny. Oh, okay.
Timing.
Oh.
Okay, sure.
Like the
Good
timing of
one.
my exam, which was 4 days ago.
We get meta jokes now.
Yeah.
Did I
Good
tell
one.
my joke or did I tell Sander's joke that I owe him?
No, this was yours.
Okay.
Yeah, you still have one more.
Mm.
Yeah, okay. Now let's get back to work. So you know you now have like building blocks with which you can do some you know elementary level compile time program. Now I'm teaching you all this because the C++ mindset about metaprogramming is that if I can push as much of my you know logic into compile time as possible, then I'm going to have a code that is all set for compile time, sorry, for runtime, and therefore I'm reducing the runtime overhead, right? And therefore that my code is going to be faster, and that means more money, because I will win in the, you know, in the comparison, right? So that's the entire reason why that initially became a thing, because C++, like C, has always been very thirsty about performance, right? So that's that. But then later on, people realized that there is another angle to compile time metaprogramming that is very important. The thing is that if you can catch errors, if you can catch bugs at compile time, then your production code is less buggy, and therefore, you know, your code remains in the business for a longer time, and you need to provide less maintenance for it, which again means more money, right? So those are two reasons why in the C++ community you have the tendency of doing as much possible as at compile time. Now, unfortunately, because the C++ syntax for you know, template metaprogramming is coincidental, it's you know, it's very horrible. There is a proposal for a better C++ syntax. The proposal didn't really manage to make its case. At least it hasn't still managed to make its case. It's been around for 4 years now. I don't know. I'm not aware of, you know, more recent versions of this proposal, but this is I mean, in Remarkable you won't be able to see it, but if you see the PDF, then you would see that there is a link here, so you can see the proposal. Now, I as a programming languages person, I have to say that the proposal wasn't that that remarkably better. It was better to a certain extent. It helped a lot with what C++ people are used to seeing, so it reduced a lot of the noise, but it's you know, it could have been much better. Now, so the other thing that I need to tell you is that, and I think that this is something that I have already told you a number of times, C++ template metaprogramming is like a language of its own, even though it was never planned to be that. It's like a language of its own within the language C++. That by coincidence is pure, and it's dependently typed, right? We have seen most of what I just told you, but we're now going to see more. So let's say that you wanted to have a function which takes a number p, and it you know, it works out whether or not the number is prime, right? Now, here's the Idris pseudocode. Well, now I'm putting this here because I'm trying to say that we want this to happen at the meta level, right? But this is my syntax. This is not Idris, right? So I'm trying to enforce that this entire, you know, computation needs to happen at compile time. Now, Idris has something called multiplicities with which you can do certain things that I haven't told you enough about. So I'm saying that fine. Let's assume that there is such a keyword that enforces the application of the applicability of is prime at compile time. Now, so all it does is that it delegates the job to a helper function that starts from midway between p and 0, and tries to make sure that P is not divisible by any of the numbers within P within half of P to 0, right? Now there is a recursion, so you know it's what it does is that it takes two numbers and it says, is P divisible by D? If it is not, then it goes to one less, right? And it does that so long as you know it hits 2 for D, right? And there are a number of you know base cases down here, right? Now we are about to see this in C++ TMP, and then you will appreciate that the noise that you get there is just horrible. Now let's see. One thing that I would like to warn you about is that in C++ TMP, we always have the best fit strategy. Whereas in most lazy languages, the order of the pattern match is relevant, which means that if I move this line above these, right, then this line will catch all the instances, and I will never make it to the base cases. Whereas that's not the case about C++, as we're going to see. C++ TMP. So here you see that you know, the recursive call, right? And here is the case when it's we hit the bottom of the recursion for 2, and here is the call to the helper function. All right, now I'm going to give you a decent explanation on those, don't worry, but just for you to have the big picture first. Okay, now so let's start by the call to the helper function. Now, first of all, these things are what are referred to informally in the C++ community as meta functions, right? They are not functions. They are structs. They don't return anything, right? As structs, but they have either static data members called value when they want to return a value, or they have nested type aliases called type when they are about to return types, right? That's what is usually referred to in the C++ community as a meta function, right? Now I see some eyebrows being raised. That's perfectly normal, right? So what this is doing is that it's saying that, okay, I want to instantiate this struct do is prime with P and half of P. Now that goes and instantiates let's say this guy, okay, and well, this guy has a static data member called value, which we then get hold of using this colon value. Okay, now so you remember that I told you about some sort of laziness going around. The laziness is here. This thing itself does not give us the value. in loose terms, it doesn't perform the call to the meta function. It only says, I want to call this meta function. Let me change the color. It only says, I want to perform this meta function call. Well, I want to perform a call to this meta function with these arguments. But the call is not performed until we look up the value data member. Right? That's the kind of laziness that I was alluding to. Right? Now, so one more thing to notice here is that the logic is completely lost in the syntactic noise that we get. Come on. No. So in the Idris code, you just, in the Idris code, you just get your signature and your cases. The logic is relatively clear. Whereas here, there's a lot of syntactic noise going around, which hides completely the logic. Right now, I'll give you 1 minute to have your piece with this piece of code, and I'll add one thing. The specializations are here. Right now, leave the specialization. So the case of the special case of 0, 1, 2, and 3. 0 is not prime, 1 is not prime, 2 is prime, 3 is prime. Right now, we'll get to this part later. So forget about the special cases. Forget about the special cases. Just try to follow the logic, and you have 1 minute. Now, if you can follow the logic, there still is some syntax in here that I should explain to you. Are we all able to follow the logic and spot it out of all the syntactic noise that is around? Anyone still needing time? No? Okay. So what is that static doing there? And what is const expert doing there? Well, I think const expert thing you probably remember from the previous session. So const expert is trying to enforce the availability of these value data members at compile time. So that's const expert, right? Now the static thing is something I haven't told you about, and this is more of C++ itself than C++ template metaprogramming. So let's say that you have a struct S. Your struct can have data members. Let's say that I have an integer data member, which means then if I have two instances of S, right? Each instance of S has its own data member S, well, S.I, S1.I. So I can do things like these, right? But you can also have static data members. So let's say that I am going to call this static data member, right? Now, oh, sorry. So let's say static float F, right? Now, then when something is static, it belongs to the class or to the struct rather than to the instances, right? Which means that I wouldn't be able to do, let me just write this one in red. I wouldn't be able to do S1.F because F does not belong to S1. And in the same way, I wouldn't be able to do S2.F because F doesn't belong to S2 either. S belongs to the class. It's shared amongst all the instances, right? What I can do, therefore, it's that I can access it through the class, and the syntax for accessing it through the class is by : : and with all of that, so when we mark this static, and let's see the guy. Now, so it's because we are now marking it static that we can, or we should, use : and then value here. Right? Now, here is a question for Jan. Why do we want to call this, why do we want to make this static?
So it doesn't change at runtime?
Yeah, that's one thing, but changeability is the, I mean,
Mutability, I guess, yeah.
The thing is that it's whether or not you can change it is a matter of the usage of const expert. The mutation, the possibility of mutation, the mutability is something that we work on using const expert.
All right.
Staticness provides us something else. Niels wants to say. Okay, Niels.
Is it because if we know that is prime of 13, then, or if we create an instance of that, we know that all instances of like is prime is 13 is true, so we don't need to check it for other
prime numbers.
Yeah, so no, like if
prime 13.
if we had other instances of is prime 13, because with the example you gave where you had S, so if S like took in or if it was is prime 13 of S1 and S2, then we know.
So we want to, I think what you're trying to say is that by doing so, we perform it once for every instance of the struct. Is that what you're saying?
Yeah, of the same, with the same number.
Right. Well, that was a very interesting thought. I have never had that response, but I'm afraid the answer to your question is no, in the sense that this wasn't the intention, but your observation is right. Now, James.
I'm pretty sure the reason you want the static there is because if you didn't have it, then it would always call the same value constant expression from the specialization that you instantiated it with. And so to get it to reevaluate which struct to take the value from, you need to do a you need to call a static value instead of instance value, or else it will go into itself.
Your thoughts are along the way of the same way with Niels, but that's not really the intention. So the intention for these structs, first of all, is that these structs, but they sorry, not there. So do is prime and is prime. They are not meant to be instantiated during the runtime. They can. There is nothing preventing people to instantiate. Oh, Niels, right? Okay. There's nothing preventing them, preventing anyone from instantiating them. But the thing is that it's that's not the purpose. The purpose is compile time metaprogramming. Right? Now, so we want to have something we can deal with at compile time. Sure, I read your comment, Niels. No problem at all. Now, so what we are trying to achieve here is that we're making it static so that the computation takes place at compile time.
Okay.
Because the computation of the static needs not to wait for instances to arrive at runtime so that it takes place.
Because by
Which
declaring
means,
it as
by
declaring it as static, does that mean that we declare it as being statically typed? So all the type, all the type level
statically typed? No.
Okay.
No, there's nothing related to static typing versus dynamic typing here.
All right, yeah, everything is statically typed in C.
Yes, in C++, everything is statically typed. Right. Now, what that means is that, so if I call a, this is not a call, but if I write is prime, well, the lucky number here was 13, right? So this expression, oh, this is not beautifully written, so right? This expression reduces to true at compile time, right? Because this static data member does not need to wait until runtime for it to be acquired. And the compiler needs to acquire actually that data member at compile time because it is shared between all the instances. Because every instance, when it is created, needs to have access to this static data member. So with that in mind, and with C++ people knowing that, they made use of the language and it's this feature of it so that they can enforce the computation to take place at compile. Now remember, static existed before C++ template metaprogramming in C++. It was only discovered to be useful for this purpose. And that's what I meant by people, being ready for shedding, sweat and blood and tears for getting things done at compile time, right? Now, luckily, and I get it that you, so I'm guessing that you guys can now understand that these lines of code you can understand. Yeah. Okay. Now, the order of these lines of code does not matter in C++. So you can shuffle around these as you wish. So you can, for example, put this above the 10th one, and in fact these specializations can even come before all these no, the specializations cannot come before the main one, but the order of the specializations is unimportant. So that's something you have to be careful about with respect to the match strategy of C++. So in C++, templates are always overload resolution and likewise the matter of specialization resolution is always based on the best match rather than the order of appearance and the source code. Now, we have already had 5 minutes, more than 12. I think not much is remaining. No, there is a lot remaining. Okay, then I should stop here. I should stop it. Okay. Any question?
No, not really. Not. It comes to mind straight away. Right.
I have one question for you now that we are stopping here. Tell me which phase. So you remember that the C++ templates enjoy this this thing that is called two-phase translation, right? Now let's say that I have forgotten this case, right? And I asked for is prime of 3 value. At which phase will the instantiation fail? And remember that we have, oh, sorry.
Can we look at the other code?
This code, you mean?
Yep. This is what it
Sure. So here's a hint. The first phase is about catching errors that do not depend on the template parameters.
Yeah.
The second phase is about catching errors that do depend on the template parameters. So which phase?
I'm just trying to work out if it will fail. I'm sure it will fail, but I'm trying to work out where it will fail.
Okay.
That's why I'm trying to follow it through.
Right. Sure.
because you give it the 3 and then
Yeah.
it goes 13.
No. This is.
Oh yeah, sorry, the 3,
This is for before.
and that will trigger 17. That one. So then it will
Yeah.
recurse to 3, 1.
That's right.
And so it will go up to 2. And then
It will go
line
up
2,
to
line
line
2,
2. Yes.
and do that one.
Sorry.
And then it will go p mod, that's the word, 1. It's not equal 0, which will be false. So it won't fail. It will just give you the wrong answer.
That's it.
I thought so. Trick question.
Mm.
Oh, it might fail if but it should short circuit, so it shouldn't evaluate do is prime.
Correct. Yeah.
But I don't know if it will, because it might want to preserve.
It does short
Short
circuit.
circuit.
But does that mean it won't evaluate it? I can't. I think it will have to evaluate it so that you have bottom preservation.
Evaluate this part.
I think it will have to evaluate it because it does want errors to come up, doesn't it? It wants to at least type it. Because I'm pretty sure.
No, well, it will do phase 1 on it, but not phase 2.
Yeah. So let's check
But
phase
the phase
1.
one, the phase 1 is done. So it won't do phase 1 on this call because it's not making that call. Right? It will do the phase 1 to this.
Yeah.
It will
It
do
will.
phase 1 to this, which
Yes.
which will not notice any mistakes.
Yeah.
Okay.
And
then so 3 mod 1 is equal to 0, right? Therefore, this becomes false, and it short circuits, as you said, and it will return false, and that's it. It will just give us a false result. There is no compilation failure. Right, but that's not what I wanted.
I just wonder though, because that it kind of seems insane in a way, because if you say you carried on, say it didn't short circuit, then you do p of d minus p, do is prime p and 3 and 0, which means you'd end up back in there, and then you'd be modding by 0, which would be an error, because you can't mod by 0, can you? Surely
No,
not.
You can't. No, you can't.
And I think you'd want that error.
Well, that will produce a compile time error, yes. Because because
it's strict, because the language is strict, I know it does short circuiting, but in order to have any kind of semantic consistency, the whole thing should error.
Well,
because it's invalid if you look at the semantics of your program. So the fact that it doesn't error seems problematic to me. Because it's not a lazy language.
C++ is not a lazy language, but I was about to tell you this later. C++ TMP is lazy by default.
Okay, then I'm
selective strictness.
If it's lazy, if the
by
semantics
default.
is, but selective strictness is fine.
Yes.
Because this hasn't been selectively. You haven't said that some value depends on the second case of the and. Right. Because so I'm happy. I'm happy that it doesn't fail.
Okay.
If it's lazy by default.
Right. Now, I don't know. Should we take that to be the happiness that the happy ending that we should have had, or should I give you even more happy ending by
You can
telling
give
you
another
that
happy
nowadays?
ending.
What was it, sorry?
You can give another happy ending. You can go
Oh, I
double
can.
happy.
Okay.
Yep.
Okay. So in today's C++, you don't need to go through all that syntactic noise in this very specific case, because we can just have an is prime function which is const expr, which means that if P is provided at compile time, the result will be produced at compile time. And you can even go past the recursion. You just put a for loop in and you get the logic done without being a pure functional language. Right?
I am happy, but I will say I do like the nonsensical splitting of. I do like it. I like
Well,
it
because you're a functional program, but remember
because I'm
that
a
most
functional
people,
programmer.
yeah, but you can, there's nothing preventing you from still doing it at the functional way, in the functional way, right? So you can implement this is prime function in a functional manner, right? And don't go through the for loop, right? That's absolutely possible. And if you even in C++23, even if you want to enforce it that this call has to happen at compile time only exclusively, you can replace that const expr by const eval, and that will be exclusively available at compile time. And what I was saying was that you can get the syntax away. You can get the noise away, right? But in addition to taking the noise away, because we are dealing with C++ programmers, and C++ programmers often consider recursion hard, the language has given them the possibility of also doing const eval and const expr things. Not everything, but a lot of it is now available. You can do your routine C++, which typically is not functional at the const expr and const eval times. That's what I was trying to say.
Do you want to make a proposal, by the way, for different syntax? Because I saw a different syntax for C, which was really interesting. Because what it did is it took schemes macros and dragged them kicking and screaming over C. And what you were left with is much, much kinder on the eyes somehow than C++ template metaprogramming. And you can do things
tell me
like
about it.
define, you could do define syntax as well, because it was essentially scheme, just with curly brackets. And there
are loads of things which called hygiene macros. So I mean, the different people have different senses of hygiene macros.
Scheme is definitely write-only code, or at least it's very important in Scheme that nobody out of your team can work out what your code is doing. It's very important.
Yes.
Very important.
Yeah. Okay. So now I'm going to stop. I needed to go stop share.